Hello, class. This is a continuation in a series of lessons on stoichiometry. In the last lesson, we discussed molar mass and gram and mole conversions. In this lesson, we're going to talk about percent composition of compounds and hopefully start on some empirical formula calculations. Before we do that, something we need to make sure we memorize are the gens, which are my diatomic elements, meaning two atoms. So hydrogen, oxygen, nitrogen, and the halogens all exist as diatomic elements, meaning in nature they are never by themselves. They always exist as a pair. H2, O2, N2, F2, Cl2, Br2, and I2. That doesn't mean they can't be by themselves when they are part of a compound. It just means when they exist naturally as elements, they exist diatomically. That is something you need to memorize because when it comes to writing balanced equations, or if a problem tells you that you're dealing with oxygen gas or nitrogen gas, they're always referring to O2 or N2, not O and N. So it is something to keep an eye out for. There are some other forms of elemental atoms that are different from what you would expect on the periodic table. You won't see these ones a ton, but if you're in a college chemistry course, they may refer to these and expect you to know them. P4 is the tetratomic form, tetra meaning four, of elemental phosphorus. It is one of the allotropes of phosphorus. We also have S8, which is an elemental form of sulfur, which is also an allotrope. And then with carbon, there are a lot of different covalent networks that exist for carbon. We have graphite, we have diamond, there are even buckyballs, which is really the common name for Buckminster fullerene, which is essentially a sphere of carbon, which is really interesting. Anyway, in this lesson, we're primarily going to talk about percent composition of compounds. So there's two ways to describe chemical composition. You can look at the number of each type of atom in the formula. So by looking at the subscripts, like CO2, I have one carbon and two oxygens in one molecule of CO2. Or you can look at the percentage by mass of the elements in that formula. So the law of constant composition states that any sample of a pure compound always consists of the same elements combined in the same proportions of mass. So when we go to do a percent composition calculation, essentially all that means is that the mass of a desired element over the total mass of the compound times 100% gives you your percent comp, or your percent composition. So we're going to look at our first exercise here, dealing with carbone, which is a substance that occurs in two forms having different arrangements of atoms with the same molecular formula and mass. One type of carbone gives caraway seeds, their characteristic smell, and the other type is responsible for the smell of spearmint oil. Calculate the mass percent of each element in carbone. So first, we're going to need our molar mass. So before we can do percent comp, we got to find the entire molar mass of this. So here we go. I know I've got carbon's mass is 12.01 times 10 carbons plus 1.01 for hydrogen times 14 of those plus the mass of one single oxygen. So the total mass of carbone is 150.24 grams per mole. Now, to find the percent comp of each element, so percent comp of carbon, we're going to take that first portion, 12.01 grams per mole of carbon times 10, divide that by 150.24 grams per mole, and then multiply by 100% to figure out our percentage. So it's basically looking at each part of a whole. Not a terribly hard calculation, but can get tricky sometimes. So divided by, and I'll just plug in my answer, 150.24. So that looks like 0.7993. If I multiply that by 100%, The bulk of this compound by mass, 79.9, I'll round up to 2 decimal places. 79.94% of this compound by mass is carbon. And then we can repeat the same process for hydrogen. 1.01 grams per mole of hydrogen times 14 divided by 150.24 grams per mole. And then again times 100%. So we've got 1.01 times 14 divided by 150.24. This one, 0.09411, so times 100. This is 9.41% hydrogen. That was a terrible 9, excuse me. 9.41% hydrogen. So this is interesting to look at because even though there's more atoms of hydrogen, because it has a smaller mass, the overall percentage of hydrogen in the compound is much smaller. So only about 9% of this is hydrogen. And then the last one we'll do is oxygen. So we've got 16 grams of oxygen over 150.24 grams per mole. Again, I should have put mole here, I'm sorry, grams per mole times 100. And 16 divided by 150.24 times 100. And that's a really interesting figure too. So 10.65% oxygen. So believe it or not, there's actually more oxygen by mass than hydrogen, even though there are way more atoms of hydrogen in my compound. Now, something to note, depending on your rounding, your percentages at the end, may not always add up to 100, but they will be very close. So you can always check 9.4 plus 9.41 plus 10.65. This time it did add up exactly to 100, even with me rounding to 2 decimal places, but sometimes it might be like 99.98 or something like that, and that's okay as long as you set up your problem correctly. Okay, so go ahead and try the percent composition for penicillin. This one I gave you a decent amount of space because you have 1, 2, 3, 4, 5 elements that you have to do that calculation for. All right, welcome back. So determining the formula of a compound is our next topic, and we're only going to get into the first type, I think, in this video. There are 3 types of empirical formula problems we're going to look at. The first type is using percentages or percent compositions, which we just discussed, to figure out the empirical formula, which is the simplest whole number ratio of elements within a compound. We can also find molecular formulas, which are the actual number of elements within a compound. This is usually a multiple of the empirical formula. What that means is that the mass of our empirical formula is the least common multiple of the molar mass of the molecular formula. So, for example, sugar we know has a formula of C6H12O6, and it has a molar mass of 180.18 grams per mole, roughly, depending on which values you use and how you round. But then if we look at its empirical formula, which is the simplest whole number ratio, I can divide the C by 6, I can divide the H by 6, and I can divide the O by 6 to give me a CH2O as my empirical formula. So essentially what I did here, divide by 6, divide by 6, divide by 6. This turns into 1, 2, and 1 is my simplest ratio. Okay. So because the molar mass of CH2O is 30.02, if you divide 180.18 by 30.02, you have roughly 6 units of your empirical formula that make up your molecular formula. So that is something to keep in mind. The first problem type, as I mentioned, is going to have to deal with percentages. So we're going to assume we have a 100-gram sample of our compound. because percentages are out of 100. So if you are given a 71% carbon in your sample, you can assume you have 71 grams of it. And that's just going to make life easy. Once we have our percentages and we've assumed them to be masses, we'll convert those masses to moles. Then we're going to divide by the smallest amount of moles in our set. And the reason we want to do this is so that we can get a simple whole number ratio. That whole number ratio will be your subscripts in your empirical formula. If you divide by the smallest moles in the set and you don't get whole numbers, that's okay. We just have to multiply by a factor so that way we can get rid of any decimals and we end up with whole numbers because subscripts can only be whole numbers. So let's go through and try that here. They give us these mass percents for carbon, chlorine, and hydrogen, and we want to figure out the empirical formula and the molecular formula. They also give us the molar mass here. So the first part, percent to mass. So I've got 71.65 grams of chlorine, and I'm going to convert that to moles of chlorine. Now, this is just a single amount of chlorine, not diatomic. I know that's a common mistake because you see chlorine and you say, oh, that's a diatomic element. I should divide this by 70.9 because that's the mass of chlorine times 2. No, you only have to deal with specific element masses on here. You don't have to worry about diatomic elements with empirical formulas. Let's see. So we got 24.27 grams of carbon, 1 mole of carbon, and 12.01 grams of carbon. Again, I'm just doing I did percent to mass, so I'm assuming I have grams of all of these, and then I'm working on the mass to mole step, converting all of these from grams to moles. So 1.01 grams of hydrogen. Same deal with hydrogen. That's normally diatomic, but in this problem, you just need the regular mass. Okay? So then we're going to go through, figure out each of these, 71.65 divided by 35.45. And that gives me 2.02. And those are considered to be moles, 2.02 moles. We've got 24.27 divided by 12.01. This is also roughly 2 moles. And 4.07 divided by 1.01. And we get, 4.029. Now, a note here. Again, it's not going to be exact. So this is Cl, C, and H. It's not going to be an exact number most of the time. This multiply till whole step really matters if you see decimals that have common fractions in them. So like 0.5 is 1/2. That is something you would need to multiply out to get rid of the half. 0.333 repeating is 1/3. You would want to multiply all of your set by 3 to get rid of that number. In this case, we're probably not going to have to do that, right? So we're going to go ahead and divide by the smallest amount here. So divide by 2.02, which is our smallest amount. It is the same for carbon and chlorine, just by happenstance, and that's okay. Dividing by the smallest amount, we get 1, 1, and this is going to be about 2. And that's okay. 4.029 divided by 2.02. You'll see again, it's 1.99. I'm just going to round that to 2. If it's really, really close, it's okay to round. If it's, again, 0.333 repeating or 0.5 or something of that nature, those are easy fractions we can multiply out. So here I've got whole numbers. I don't need the multiply till whole step. I've got 1 chlorine, 1 carbon, and 2 H's. So my empirical formula is CCl2, or CH, sorry, I should put this in proper order. Typically you put hydrogens first after the carbon. So CH2Cl2 is your empirical formula here. This is the empirical. Now, I need to find the mass of this and compare it to the mass that they gave me of 98.96. So I've got 12.01 plus 1.01 times 2 plus 35.45 times 2. And, oh, I'm sorry, I only had one chlorine here. I just realized I made my mistake here. Right, I have one chlorine, one carbon, two H's. So CH2Cl is the empirical formula. My bad. Let's go back and calculate that again, but take that 2 out. Aha. So the empirical formula has a mass of 49.48 grams per mole. So to figure out the molecular formula, I'll do 98.96 divided by 49.48 grams per mole in order to figure out how many times I have to multiply my empirical formula to get my molecular. So 98.96 divided by 49.48, that is 2. So my empirical formula is CH2Cl. My molecular here is going to be C2H4Cl2 because I have to multiply each of those subscripts of 1, 2, and 1 by 2. And that is how you figure out the empirical and molecular formula for a compound. Go ahead and try each of these problems. I think I gave you 2 of them here for type 1. And I think we're short on time here. Yeah, I don't have time to do a second one in about 4 minutes. So that is going to be all for this lesson. In the next one, we'll talk about type 2 and type 3 empirical formula problems. Those ones particularly deal with finding empirical formulas from combustion analysis. So we're going to have to look at masses of other compounds such as carbon dioxide and water, and then use those to figure out our empirical formula. And then we're also going to look at empirical formulas of hydrates. Typically, the first lab of AP Chem that we have our students do is finding the empirical formula of a hydrate. So doing a problem like this will actually prepare you for an upcoming lab. All right, that is all for this lesson. See you in the next one.